properties of dwarf spiral galaxies. So, first, before explaining you about my research, let me introduce you to some definitions that I'll be using throughout my presentation. Magnitude. Magnitude of an object is the brightness, a measure of brightness. So if you have higher values of magnitude, that means you have faint objects. And if you have lower values, that means you have bright objects. For example, we all know that sun is a very bright object, and it has a magnitude of -26. The color. The color is not the color that we use everyday life, but it's the difference between two filters. So the filters, there are different types of filters that we use in astronomy. Ultraviolet, blue, visual, red, infrared, and all of these filters are visible filters. So if you have similar values for objects, that means you have similar colors. And the next is the metallicity. Metallicity is the proportion of elements that are heavier than hydrogen. So in our case, metallicity was estimated using the absolute B-band luminosity. So there's a linear relationship between the absolute B-band luminosity and the metallicity. So what are these dwarf galaxies? Dwarf galaxies are very faint and they're smaller compared to other bigger galaxies. Like if you compare it to the Milky Way is about 100,000 light years, and as opposed to that, a dwarf galaxy is about less than 45,000 light years. So it's pretty small compared to a bigger galaxy. And the brightness of a dwarf galaxy is defined in various ways. So in literature, according to Ramsey, they are fainter than -18 magnitudes. According to Roberts and Davis, they are in between -14 and -10 magnitudes. And according to Hodge and Taman, they are fainter than -15 or -16 magnitudes. And there are three types of dwarf galaxies: dwarf spiral galaxies, dwarf elliptical galaxies, dwarf irregular galaxies. So let me explain to you more about these three types. So the first type is dwarf spiral galaxies. So as you can see, they have a spiral arm structure. So you see here a spiral galaxy. It is not a dwarf galaxy, but I just wanted to show you the shape of the dwarf spiral. So they have low luminosities and small diameters. Usually they are less than 5 kiloparsec. 1 kiloparsec is equal to 3,000 light years. So that means they are less than about 15,000 light years. And they also have a low surface brightness, and they are hydrogen-rich galaxies. The next type is dwarf irregular galaxies. These type of galaxies have no particular shape to them, unlike the one I showed you earlier. They have no nuclear bulge or a spiral arm structure, and they are also hydrogen-rich. The third type, dwarf elliptical galaxies, are usually fainter than -16 magnitudes, and they are elliptical or spherical in shape. And they're also hydrogen poor. So you see elliptical galaxy over there. And so these dwarf ellipticals and dwarf irregulars have been found to overlap in both surface brightness and their color. And also, according to Moore et al. And Masterfield et al., these dwarf irregulars have evolved into dwarf ellipticals. But in contrast, Gribble et al. Has stated, no, they are not evolved, dwarf ellipticals and spirals are not evolved from dwarf irregular galaxies, but transition galaxies. So there are various theories they have put forward about the evolution. So, and dwarf spiral galaxies and dwarf elliptical galaxies also have been found to be related to each other. So, moving back to transition galaxies, these transition dwarfs are simply dwarf spirals that keep their gas. So, therefore, the question of whether or not transition galaxies are evolved from dwarf regulars remains to be answered. So, what are we really looking for? Do these target galaxies actually meet the criteria to be considered dwarf spiral galaxies? And is there any similarity in the range of color and surface brightness profiles of these dwarf spirals and irregulars? And so, galaxy color represents the galaxy's evolution. If you have bluer systems, are younger, and redder systems are older. So if you have overlap in the color, that means there is some evolution link. So there's a possibility that one evolved into another. So we are basically looking for an evolution link between the types of galaxies. So let me show you some previous work and what we have found in my previous research. So we collected our data at the Dunn Observatory using 82-inch telescope, and we made sure that our target galaxies are less than 15 kiloparsec, that is 45,000 light years, and we corrected them for absolute V-band. And in this way, we analyzed about 20 dwarf spirals and corrected them for bias current and flat filtered them. Because, so if you take a galaxy, if you image a galaxy, you can't use it as it is. So you have to make some reductions and do some bias subtractions, flat filling, and sky subtracting to get that this clear image as opposed to this raw image. So final result is that you get this image to analyze it further. And these images were calibrated using interactive data language and image reduction analysis facility, and also photometric data were also measured. And the surface brightness profiles for these galaxies were also constructed, and this was accomplished by fitting the shape of each galaxy in a row with an ellipse and measuring the amount of light present in each ever-expanding ellipse as it moves outward from the center. And here you see, so this chart shows you the color of the three types of galaxies, comparison of colors. So if you see here in this region, the color, there's an overlap in the color ranges. And even if you move on to the absolute magnitudes, in that chart also, there's an overlap in absolute magnitude for all of these three types of galaxies. And the radius also overlap. But the problem was when you compare the distributions for these three types of galaxies using the case statistics, it showed us that their samples are very different. So previously we couldn't really conclude that they are related to each other, although that we had results showing that there are overlaps in color and their sizes. So now you have seen my previous work. So let's move on to my current work, what I'm doing right now. So now I'm looking at the star formation histories of dwarf spiral galaxies. So I'm basically comparing the star formation history of a dwarf spiral, the real data with the model star formation history, which was produced using the Pegasus evolution code. So what I did here is I input the star formation rate and the frequency to this code, and Pegasus would evolve the stellar population. And I can look for the best matching scenario, and as well as whether if a small change in parameters is still a good fit. So let's look at the results. So in this plot, you see the star formation history of UGC 6007, which is a dwarf spiral. So here, in y-axis, you see periodicity burst in mega years, and x-axis, in x-axis, you see the time. And this plot shows you how stars have evolved in this galaxy. So the green dots are better fits. That means it represents the color of these galaxies better, and it represents star formation histories better. So if you have larger and green dots, that means it's a good fit. It represents the true, it's very close to the true star formation history of that galaxy. And it's with the true metallicity value. The next shows you the star formation history of the same galaxy, but I changed the metallicity value of the galaxy. As you can see, this also looks similar to that. So if you compare the two, they're both basically the same. So you see in this galaxy, the stars in this galaxy are either old or younger, but somewhere in the middle. And what we can say from this is that, so there is no effect in changing metallicity value. So that means this code is not very sensitive to the changes in metallicity. So next you see the first star formation history of UGC 6007 with its true metallicity value, and I'm comparing it to the another plot of star formation history of the same galaxy, but there's a difference in second plot because I allowed the metallicity to evolve over the years as opposed to keeping it constant. So in the first one, it had the metallicity has its true metallicity value, but it's constant. But in the second plot, it has evolved over the years. And by the way, it was a mistake, but still we got something out of it. And so these two plots are also basically the same. So that means the code is not very sensitive to the evolvement of the metallicity either. So in conclusion, these galaxy colors are well represented by all models considered, and Pegasus code is not very sensitive to changes in metallicity values, or it is not sensitive to allowing the metallicity to evolve over the years. So in future, we hope to fit star formation histories of those spirals that we have imaged, because at present we only looked at one star formation history. So in future, we hope to plot more of these for other galaxies. And the next is to improve the accuracy of our brightness measurements. This can be done by getting H-alpha imaging, hydrogen alpha imaging. So by that, you can locate the foreground stars in the galaxy and subtract it from the image, the galaxy's image, and get a better measurements, brightness measurements for our dwarf spiral galaxies. So that's all I have for now. And we would like to thank Midwestern State University for funding this research to Weerasooriya as well as to the physics program. And special thanks goes to Dr. Jacqueline Dunn, Dr. Rinkan, Edward for their immense support. Images were obtained by the Magellan Observatory, operated by the University of Texas Austin. This research has made use of the NASA Extragalactic Database, which is operated by the Jet Propulsion Laboratory, California Institute of Technology, under contract with the National Aeronautics and Space Administration and the Sloan Digital Sky Survey. So these are my